This video is the sixth of a series of tutorials discussing the LX7720 radiation-hardened motor driver for space. First, here's a reminder of what the LX7720 actually is. The LX7720 is a mixed-signal peripheral which works with an FPGA, or a microcontroller, to build a complete closed-loop brushless DC motor controller or stepper motor system. The first two videos outlined the LX7720 at a system level and then dived into a detailed discussion of the half-bridge FET drivers. Videos 3 and 4 introduced the LX7720's 4 current sense amplifiers and showed how to use a current sense amplifier in each of the 3 common current measurement topologies used with motors. Video 5 discussed separating a half-bridge into independent low-side and high-side drivers and how to use current sensing in these cases. This video discusses connecting an LX7720 to a brushless DC motor or a permanent magnet synchronous motor with optional electromagnetic brake. The LX7720 contains 4 half-bridge driver stages and 4 current sense amplifiers, which is enough to drive a 3-phase synchronous motor. Motor types include permanent magnet synchronous motors, or PMSM, and brushless DC motors, or BLDC. PMSM and BLDC are both permanent magnet-based motors with the permanent magnets on the rotor. The stator contains equally spaced Y or delta-connected windings, 3 for a 3-phase machine. PMSM and BLDC motor design varies in detail and also in drive waveform, sinusoidal versus trapezoidal or triangular. However, the basic architectures are the same as far as the half-bridge driver stages are concerned. Here's a generic 3-phase motor being driven by 3 half-bridge drivers with current sensing in each phase drive output. The motor is shown with a Y or star stator winding type, but the connections to a motor with a delta stator winding are the same. The LX7720 circuitry is shown simplified, with supplies and decoupling to the current sense and gate drive sections omitted. The key components are the 3 half-bridges and the current sense. All 3 winding drivers are shown with current sensing in the phase outputs. However, since current entering one phase has to exit via the other 2 phases, only 2 current senses are actually required. The third phase current can be calculated from the sum of the other 2 currents, including the third current sense circuit, which provides redundancy if required. The half-bridge FETs are shown with their integral body diodes. Diodes in parallel with the FETs are necessary components to carry commutation currents when a half-bridge FET switches off. Commutation current flow after FET switch-off is discussed in detail in the 4th video. The FET body diodes are often paralleled by discrete diodes for higher switching speed and lower voltage drop. Motor winding currents flow between the motor supply, VMPS, and the motor ground, M-ground, through some combination of half-bridge FETs and/or commutation diodes in parallel with the FETs. The LX7720 uses 2 internal ground domains, shown here as the signal ground, S-ground, and the motor ground, M-ground. S-ground is used for the digital and analog signals, the control circuitry. M-ground is used for circuitry associated with the external half-bridges, the FET drives, current sensing, and the motor load itself. The level shifters manage the crossing of the ground domains. If a motor controller board design locates the motor drive power section, the half-bridges and commutation diodes, on the same PCB as the LX7720, then the 2 grounds, S-ground and M-ground, should be joined together directly on the PCB and therefore will be at the same potential. For high-power motor designs, it can be more practical not to route the VMPS high voltage and/or high current paths on the controller PCB. In this case, the power switching components will be on a separate module, or PCB, usually near the motor. With this separated architecture, the motor supply VMPS and its associated return P-ground take a separate path to the half-bridge FETs via a wiring harness. The LX7720 still needs a connection to the motor supply VMPS because this is a reference for the high-side FET drivers as discussed in the first video. The LX7720 also needs access to the half-bridge driver's ground. These two signal interconnections are shown in red here. Note that now S-ground is not directly connected to M-ground, but relies on the system ground path external to the PCB that the LX7720 is on. However, since the motor's power winding is carrying the high current motor waveforms, there will be ground bounce between the linked P-ground and M-ground, and the LX7720 signal ground, S-ground. The maximum allowed potential difference between the LX7720's M-ground and S-ground is minus 10 volts to plus 8 volts, so grounding is important. If analysis of the end system shows that this might be exceeded during transients, a back-to-back Zener diode pair between S-ground and M-ground may be enough to clamp these occurrences. Synchronous motors are also available with more than 3 phases. Since the half-bridge and current sense stages are independent within an LX7720, multiple LX7720s can be used together to control a motor with more than 4 phases. In the case of a 3-phase motor, the LX7720 offers one spare half-bridge stage. The 5th video discusses separating a half-bridge into independent low-side and high-side drivers with optional current sensing. However, loads such as solenoids or an electromagnetic brake are often driven with a PWM waveform to regulate current and therefore mechanical force. PWM timing is adjusted on a cycle-by-cycle basis by monitoring the rise and fall of output current in the inductive load. Here's a low-side driver with high-side current sensing. When the low-side switch is on, load current passes through the current sense resistor. When the load switch turns off, the diode provides a path for the inductive load current to ramp down. Diode current also passes through the current sense resistor, so this arrangement allows load current to be measured continuously, whether ramping up through the FET when the switch is on, or ramping down through the diode after the switch is turned off. The alternative configuration, shown here, is a high-side driver with low-side current sensing. The current sense could be performed instead by a spare ADC input if available in the system. In that case, 2 load drivers can be built with just one spare LX7720 half-bridge section, reserving the LX7720's current sense block for the low-side driver. These 2 drivers have 2 disadvantages. Firstly, 2 wires are required to connect the load. Secondly, the diode, D, is relatively lossy. Both these limitations go away by simply using the complete spare half-bridge to drive the load, with current sensing positioned in the output. The high-side FET drives the load, and the low-side FET operates as an active diode. The extra half-bridge is configured the same way as the other 3 used for the motor, perhaps with detailed differences in the power components. There is one caveat to bear in mind. The VGS gate supply and VMPS motor supply are common to all 4 half-bridges within an LX7720. This means that the solenoid or electromagnetic brake must use the same VPMS and VGS supplies as the motor with all 3 alternative circuits. Finally, here's how to connect either an unused half-bridge driver or a current sense amplifier. We hope this video has helped you understand connecting the LX7720 to brushless DC and permanent magnet synchronous motors. In our next video, Episode 7, we will discuss connecting an LX7720 to a bipolar stepper motor.